Howdy. This video is on isomers. Two compounds can have exactly the same chemical formula, but a different arrangement of atoms leading them to isomers. Isomers can have slightly different chemical and physical properties. Hopefully after watching this video, you can determine all the isomers for a given chemical formula and list what kind of isomers they are. Hopefully you can identify the different types of isomerisms. And so isomers in general are composed of the same exact set of atoms. They have the same molecular formula, but something else is different. So for instance, for structural, also called constitutional isomers, they have exactly the same set of atoms, but have different types of bonds. Stereoisomers have the same sets of atoms, same types of bonds, but different relative orientations of the bonds. Now I think this flow diagram is really helpful in determining the different types of isomerisms. And so again, isomers in general, you have the same set of atoms. Structural or constitutional isomers, you have different types of bonds, even though you have the same types of atoms, same set of atoms. Stereoisomers, same set of atoms, same set of bonds, but different relative orientation. And we'll see that there are two types of stereoisomers. There's what's referred to as geometric and optical.
The molecules methyl isonitrile and acetonitrile have the same molecular formula, C2H3N. However, they differ in the bonding arrangements of the atoms. They are examples of isomers, compounds with the same molecular formula that are not identical. Isomers that have different bonds or differ in the locations of bonds within the molecule are called configurational or structural isomers. Methyl isonitrile and acetonitrile are examples of structural isomers. So also are thiocyanic acid and isothiocyanuric acid. Structural isomerism is very common in organic chemistry. For example, consider the isomers of butanol with molecular formula C4H10O. Normal butanol or N-butyl alcohol consists of a straight chain of 4 carbon atoms with the OH group at the end of the chain. In the isomer that has the common name isobutyl alcohol, the carbon chain is not straight, but has a methyl group bonded to the central carbon of a 3-carbon chain. The alcohol group is still bonded to a carbon at the end of the chain. In secondary butyl alcohol, the OH group is attached to one of the 2 inside carbon atoms in the 4-carbon chain. In tertiary butyl alcohol, the OH group is attached to the central carbon atom, which also contains a methyl group. The 4 butyl alcohols differ in their physical and chemical properties. For example, in their boiling
points. And so the boiling points go from 82 degrees to 117 degrees. And again, it's really kind of interesting. We have exactly the same set of atoms, different types of bonds, leads to different chemical and physical properties.
The molecule
Hexane is a covalently bonded molecule consisting of 6 carbon atoms and 14 hydrogen atoms. Each hydrogen atom forms 1 covalent bond, and each carbon atom forms 4 covalent bonds. These 20 atoms can be rearranged into 5 different compounds called structural isomers, each having slightly different properties. Notice how the boiling points of each isomer changes. Arranging the carbon atoms in a straight chain produces N-hexane. Moving the end carbon to the second carbon position and rearranging hydrogens produces 2-methylpentane. Sliding the methyl group to the third carbon position produces 3-methylpentane. Moving the methyl group to the fourth carbon position appears to make 4-methylpentane. But wait! Rotating the molecule shows that it's identical to 2-methylpentane. Now, adding the end carbon to the second carbon position produces 2,3-dimethylbutane. Moving the methyl group to the second carbon position produces 2,2-dimethylbutane. Sliding both methyl groups to the third carbon position appears to make 3,3-dimethylbutane. But wait again. Rotating the molecule shows it's identical to 2,2-dimethylbutane. These are the 5 isomers of hexane.
So again, they all have the same exact set of atoms, different types of bonds, makes them structural or constitutional isomers. And so here we have two more structural isomers. They both contain hydrogen, carbon, nitrogen. This one we have carbon in the center. This one we have nitrogen in the center. Now we could ask which of the following structural isomers is the most stable. And again, if we're concerned about stability of Lewis diagrams, we want to do the formal charge. And so if we look at the formal charges of all the atoms, we see here we have zeros. And so the one on the left should be really pretty stable. Here we have some non-zero values. And so remember, for formal charge, you want as close to zero as possible. If you do have a negative formal charge, you want it on the most electronegative. Well, it's kind of cool. This tells you that if you have these three atoms, most likely they're going to form the one on the left because that is the more stable molecule. We could also wonder, okay, so we have N2O. Does that mean that the oxygen is going to be in the middle, or does that mean the nitrogen is going to be in the middle? And again, if we're looking at stability, we do the formal charge. And so the one on the left, we get -1, +2, -1. The one on the right, we get 0, +1, -1. These are closer to the zero than those. And so in this case, the one on the right should be the more stable molecule. And so we should expect that when you have N2O, the nitrogen is in the center. And so you could be asked, how many structural isomers does something have? And so if you're given a hydrocarbon, and so here we have C5H12. Now, if it's CnH2n plus 2, so that means we have N carbon and 2n plus 2 hydrogen. That's what we have here. So in this case, N is 5. And so 5 times 2 is 10 plus 2 is 12. That means all the carbon-carbon bonds are single bonds. If you have CnH2n, then that means that you have one double bond or you have a cyclic group. If you have CnH2n minus 2, that means you have a triple bond, two double bonds, or a cyclic group and a double bond. And so if you're given something like this, you want to look at what is the type of molecules you could have and then try to do it systematically, seeing what you got. And so we see that we have CnH2n plus 2, so that means all the carbon-carbon bonds are single. And so then we systematically change the structure until we think that we've covered all the possibilities. And so we could put the 5 carbons in a row. We could put a methyl group off the second carbon. If you have a methyl group off the first carbon or the last carbon, it's the same as having all the 5 carbons in a row. If you had the carbon methyl group here, this carbon here, that would be the same as having it here. You just rotate around the molecule. And then we could put the methyl group off this carbon too. And so for C5H12, we get 3 structural isomers. We could also ask about C4H8. Now, C4H8, that's CnH2n. And so I mentioned that for that type of formula, you'd have one double bond or you could have a cyclic group. And so you can imagine the 4 carbons in the row, the double bond here or here. Double bond here is the same as it being there. Or you could have a double bond and then one of the methyl groups. Now for a cyclic group, we could have a cyclopropane. This isn't going to be very stable because that bond angle is 60 degrees, but still it's a possible structure. Or you could have cyclobutane. But all 5 of these structures have exactly the same set of atoms. And so if we ask about structural isomers for C4H9Cl, now if you imagine that chlorine is probably going to have a single bond, it's going to behave kind of like a hydrogen. And so that would actually give you CnH2n plus 2. And so we'd expect no carbon-carbon double bonds, and all the carbon-carbon bonds would be single. And so what you could do is actually just make the structural isomers for C4H 10 and then substitute some of the hydrogens, one of the hydrogens for chlorine. And so we can put the chlorine here. We can put chlorine on the second carbon. If we have this one, put the chlorine off that carbon and put a chlorine off that carbon. And so we get 4 structural isomers. And so structural isomers, you have the same exact set of atoms, but different types of bonds. Now the different types of bonds can be a little bit confusing. This carbon here is different than this carbon because this one's at the end. And so that makes this carbon-chlorine bond a little bit different than this carbon-chlorine bond because these 2 carbons are not equivalent. Now these 2 carbons are equivalent. And so if you put the chlorine here, it's the same as having it here, or putting the chlorine here is the same as having it there. And so when we say they're not the same bonds, the difference can be a little subtle.
Isomers that have the same groups of atoms bonded to one another, but differ in the spatial arrangements of the atoms, are called stereoisomers. In geometrical isomers, the groups are arranged differently with respect to one another. A simple example is cis-strands isomerism, about a double bond in alkenes. Because rotation does not occur readily about the carbon-carbon double bond, cis and trans 2-butene are distinct compounds with differing physical properties such as boiling point. Cis-strands isomerism also exists in coordination chemistry, as in this example of cis and trans tetramine dichlorocobalt 3 ion.
And so stereoisomers, you have the same set of atoms, different types of bonds. Different arrangements.
Have the same groups of atoms arranged in the same relationship to one another. But because the molecule lacks a center of symmetry, they are not superimposable upon one another. Optical isomers are mirror images of one another. This example shows secondary butyl alcohol, one of the geometrical isomers of butanol. Notice that all 4 groups attached to the central carbon are different. As a result, the molecule in the foreground is not superimposable on its mirror image. The 2 optical isomers are distinguished by the letters R and S. Molecules such as this are called chiral.
And so again, structural isomers, same set of atoms, different types of bonds. Stereoisomers, same set of atoms, same types of bonds, but different relative arrangements of those bonds. Now geometric isomers, here we have cisplatin, this is transplatin. So you have platinum in the middle, you got ammonia group, and chlorine. And so for the one on top, the chlorine are on the same side and the ammonia are on the same side. The one on the bottom, the ammonia groups are across from each other, the chlorines are across from each other. And so they have the same set of atoms, same types of bonds, but the relative orientations of those bonds are different. Now it's kind of interesting. Cisplatin is actually an anti-cancer drug. Transplatin is not. Another example of geometric isomers, remember you can't rotate easily about a double bond. And so this molecule actually has 2 sides. And you have the 2 chlorines on one side, 2 hydrogens on the other side. That's why you have that cis in the name. And for this one, you have the chlorine on opposite sides. And that would be why you have a trans. And so you could ask, how many geometric isomers does butene have? And so if you draw the structures, you'll see that you have a double bond. Now, you have 2 hydrogens here, and so you cannot have geometric isomers. To have a geometric isomer with a carbon-carbon double bond, the groups attached to this carbon have to be different, and the groups attached to this carbon have to be different. And so the ones attached to this carbon are different, but the ones attached to this one are not different, and so they do not have geometric isomers. So if we look at 2-butene, now the groups attached to this carbon, those 2 are different, and those 2 are different. And so that means you can either have the trans configuration or the cis configuration. And so this one does have geometric isomers. And so please remember, if you have a double bond and the groups attached to this carbon are different and the groups attached to the other carbon of the double bond are different, then it can have geometric isomers. And so for stereoisomers, same set of atoms, same set of bonds, different relative arrangements. You have geometric, which we just talked about, and you also have optical, which corresponds to having a carbon with 4 different groups attached to it.
A chiral object is one that is not superimposable on its mirror image. Your left hand is chiral. It cannot be superimposed on your right hand. Many molecules, including important drugs and natural products, are chiral. This is a ball and stick model of a carbon molecule with 4 different groups attached to the central carbon. For example, the 4 groups could be hydrogen, chlorine, methyl, and carboxylic acid. This molecule is chiral. That is, it is not superimposable on its mirror image. The 2 forms of a chiral molecule are called enantiomers. Using special rules, one form is labeled R, the other S. Enantiomers have mostly the same physical properties, but they behave differently in chiral environments. Molecules may contain more than one chiral center. For example, tartaric acid, which is found in many fruits and in wines, has 2 chiral centers.
And so when the video says it's not superimposable, it just means it's not the same. And again, so if you have a carbon attached to 4 different groups, then it's going to be chiral. Now notice it's not just the next nearest neighbor. So here you have carbon attached to carbon, carbon attached to carbon. It's the entire group. So you have to think about this carbon's attached to the COOH group. It's also attached to this group down there. And so this is a chiral carbon. This carbon here is attached to an OH hydrogen group, this group, as well as that group. And so this one has 2 chiral carbons.
A tetrahedral carbon atom with 3 different substituents is shown along with its mirror reflection. The mirror is removed and the models are compared. The model is achiral because it is superimposable with its mirror image.
So again, superimposable just means it is the same. And so this one you have 3 different groups attached to that carbon, and so it is identical to its mirror image. But here you have 4 different groups attached to its mirror, and it will not be superimposable to its mirror image. It will be different than its mirror image.
A tetrahedral carbon atom with 4 different substituents is shown along with its mirror reflection. The mirror is removed and the models are compared. The model is chiral because it is non-superimposable with its mirror image.
And so no matter how you rotate that second one, there's no way you can make it look like the first one. And so stereoisomers are really kind of interesting. They have the same set of atoms, same set of bonds, but different relative orientation. And we call them optical isomers because actually in a solution of one of the pure optical isomers, it will actually rotate plane polarized light. And so if we put one of the optical isomers, which is referred to as an enantiomer, in this container and we put plane polarized light into it, what we find is that the light was rotated. If you have a mixture of the 2 enantiomers, then we'd actually see that there was no rotation. And so the alpha carbon of all the amino acids except for glycine are chiral. And it's really kind of interesting. Only one optical isomer is present in proteins from living organisms. And so you imagine that the chemistry should be very, very similar between the 2 optical isomers. They have the same atoms, the same bonds, just different relative orientation. But you only find one of the optical isomers present in proteins of living organisms. And so a question you could be asked is, which of the following have optical isomers? And so what you're looking for is a carbon attached to 4 different groups. And so here we have 3 groups. Here we have 3 groups. Now this carbon, you have a hydrogen, a hydroxyl, a methyl, and an ethyl group. And so again, it's not just the next carbon, but it's the entire group you have to think about. So this one's going to be chiral. This carbon, you have 2 hydrogens, so that's that chiral. This carbon, you have that group, hydroxyl hydrogen, and that group, so that one's going to be chiral. This one, you actually have 2 chiral carbons. This one here has 4 different groups. That one there has 4 different groups. Does the following molecule display optical activity? And so again, you're looking for 4 different groups. So you have to draw the Lewis diagram. We see that this carbon is attached to a hydrogen, a bromine, a methyl, and ethyl. And so that would be optically active. It is chiral. For this one, if we draw the Lewis diagram, we see we have a carbon with 2 chlorines, 2 hydrogens, 3 hydrogens. It should not be optically active. It is not chiral. It does not contain a chiral carbon. For this one, so we have 3 carbons. And if we look at it, so this carbon here is attached to 4 different groups. This carbon here, you have 2 hydrogen, and so you just have 1 chiral carbon. We'd say it's optically active. It will have stereoisomers. So how many isomers does C4H8Cl2 have, and what kind of isomers are they? And so first we can work on the structural or constitutional isomers. And so we got C4H8Cl2, and so if you treat the chlorine as a hydrogen, that's going to be CnH2n plus 2. And so we'd expect just carbon-carbon single bonds and no cyclic groups. And again, we try to be systematic as possible, so we can start with 4 carbons, put a chlorine at the end, the second chlorine here, 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 and here. So we have 4 structural isomers. Now we could also imagine that we put the chlorine in the second one, and so then we can also put it up there. And we can also imagine that, okay, let's put a methyl group here, and then we can put 2 chlorines there, chlorine there, there. Or it could have a methyl group on the middle. And so that gives us 9 structural or constitutional isomers. Now 3 of the structural isomers are going to be chiral. And so if we look at those again, so this carbon here has 4 different groups attached, so it's going to be optically active. This carbon here has 4 different groups attached, so it's going to be optically active. So that's 2. This carbon here is optically active. That carbon there is also optically active, has 4 different groups attached, so that's 3. And then I think that's it. So we got 9 structural isomers, and we have 3 stereoisomers. Or 3 of the structural isomers will have stereoisomerism. We can ask how many isomers does 3-methylhexane have? And so methylhexane, that means 1, 2, 3, 4, 5, 6, methyl group there. And so notice this carbon is bound to a methyl, an ethyl, a propyl group, and a hydrogen. So it's attached to 4 different green things. And so it'll have 2 optical isomers. Remember, for each chiral carbon, for each carbon bound to 4 different green things, it will have 2 optical isomers. We could also ask about this one. And so again, notice that we have a carbon-carbon double bond. And on this carbon, 2 different groups. On this carbon, 2 different groups. And so that means, you could have these groups on the same side, which gives you cis, or these groups on the opposite sides, which gives you trans. And so that molecule has 2 geometric isomers. For each carbon-carbon double bond, you could have a maximum of 2 geometric isomers. For 2-chloro-3-methylhexane, so this carbon here, you have a hydrogen, that. So it's going to be optically active. For this one here, it has 4 different groups. It's also optically active, so you have 2 chiral centers, and so you'd actually have 4 optical isomers. For each chiral center, you can have a maximum of 2. And so hopefully you can determine the isomers given the chemical formula. Hopefully you can also identify the different types of isomerisms. Remember, isomers just means you have the same set of atoms. Structural isomers, same set of atoms, different types of bonds. Stereoisomers, same set of atoms, same set of bonds, but different relative orientations. And so for J-maker isomers, often that means you have that carbon-carbon double bond. For optical isomers, it means you have a carbon attached to 4 different types of groups. I hope that was helpful.